Module 9 is about applications of calculus, and we're going to go through one quite long example to illustrate one potential application. And the key thing in this long question is Newton's law of cooling. So this is a quite standard type of question where we use Newton's law of cooling, which is a particular differential equation. Okay, so I'll come back to this question screen a few times as we go through it, but let's quickly summarize what's going on. It's a little bit of a morbid question, sorry. Suppose that someone's been murdered, right? And their body cools from 37 to 34 degrees in 2 hours. So someone is obviously recording this happening. The temperature we're assuming is a constant 18 degrees where the body is. And we'll be able to use a differential equation to ultimately figure out what time roughly the poor person was murdered. We have to do a few things first. We want to find the temperature function, right, as a function of time. We want to sketch the graph of this function. In part 3, we want to think about what happens to the temperature of the body in the long run. So as time goes off to infinity, what happens to the temperature? And then, with a bit more information, which is suppose at 4 p.m. We observe that the body is 30 degrees. Using Newton's law of cooling, we should be able to work out roughly what time this murder happened. Okay, so we're going to start by finding the temperature of the body, the temperature function, and for that we need to know a bit of theory about Newton's law of cooling. When you're doing these questions yourself, you don't have to write down the theory, but I'll do that now as we go through this example. So recall Newton's law of cooling. So what does that say really? It says that the differential equation so d capital T, d little t, so capital T here is temperature, little t is time, is equal to some constant k times capital T minus capital Ts. Capital T S here, S is for surrounding. This is the constant surrounding temperature. So in this question, this was 18 degrees. So the differential equation has solution. So it has this general solution, capital T is equal to this surrounding temperature Ts plus some constant A, e to the k little t. Okay, so this is the general form of the temperature function in terms of time, where Ts, capital A, and little k are all just numbers. They're all constant. So our job in part 1 is to find these three numbers and then just rewrite this with the Ts, the A, and the K filled in as numbers. Now the Ts is the surrounding temperature. That's 18 degrees. So we know that already. And so the key is we go back to our question. We're given some information. We're told that this body starts at 37 degrees and in 2 hours goes to 34 degrees. So we use this information to figure out all these missing constants, all these missing numbers. Okay, so part 1, straight away let's just point out that Ts, this surrounding temperature we're told is 18 degrees. We know that if we think of capital T now as a function of time, when time is 0, this body is 37 degrees. So just purely as a function, T at the time value 0 is 37. And then if we measure time in hours, because that's what's given to us in the question, T at time equals 2 was 34. And we're going to use these two values of this function, these particular values of time, to figure out the A and the K. Okay, so we have T at 0 equals 37 implies So we're subbing into this equation. Little t equals 0, capital T equals 37. TS we know is 18. So 37 is equal to 18 plus capital A, e to the k lots of 0. Now, k lots of 0 is 0, and anything to the 0 is 1. So this turns into, thankfully, like the k term disappears. This turns into 37 is equal to 18 plus capital A lots of 1. So just capital A. And now clearly from this equation, we can figure out what capital A is. Capital A is 37 minus 18 is 19. So that's one of our constants done. We now need to figure out the little k. And so we need to use this second bit of information about the temperature at time equals 2. So we have T at 2 equals 34 means, so let's plug into the equation. The temperature is 34 at 18 plus A e to the kt. Now A we just figured out to be 19, so we can use that. E to the k times, and remember this is at time equals 2. So now we have an equation with that unknown k, and we can solve this for k. So this is more complicated than getting the capital A. So here we want to take that 18 to the left, then we divide by 19, and then we have e to the 2k, we're going to take a logarithm. Right? So this tells us that 19 e to the 2k is 34 minus 18 is 16. So now divide by 19, e to the 2k is 16 over 19. Now we want to take the inverse of the exponential function, so we take logs. So then that tells us that 2k is the natural logarithm of 16 over 19. And now divide by 2, k equals 1/2 natural log 16 over 19. Now in these questions, we're happy with taking an approximation here. So if you do that, plug that into your calculator, you get that k is approximately equal to, in this case we get minus 0.0859. Okay, so we have TS, we have A, we have K, and so we can answer part 1. So our function is T is equal to 18 plus 19 e to the kt minus 0.0859 t. That's our temperature function. Okay, so let's go back to part 2. In part 2, we have to sketch a graph of this temperature function. And then part 3, we have to think about what happens when time gets really big, when it goes off to infinity. All right, so let's graph it over on the right here. We have space. So I'll do the graph of this function here. We only want a sketch of this. So it's the basic shape is the point. And so so how do we do this? It's a messy looking function, right? So what you should know is what does the basic shape of the function y equals e to the minus kx look like, where k is a positive number here, so the negative k is really a negative. So it's e to some negative times x. So you should know this is it goes through the point 1 when x equals 0. This has value 1, and it goes off to negative infinity here, and then as x gets bigger, it gets closer and closer but never touches 0. Right, so that's the basic shape of an exponential function with a negative exponent. And essentially, we have that here. We have the e to the some negative times t. So here's my time axis, and here's my temperature axis. But we're doing two things to this. Firstly, we're scaling this by 19, and then we're shifting it up by 18, right? So when we take this basic graph at the bottom here that goes through 1, if we multiply this by 19, it's going to go through 19. And then we're shifting the whole thing up by 18, by adding 18 to it. So this is going to be 18. This is 19. And so instead of approaching 0, because we're moving the whole thing up 18, the graph is going to have the same basic shape, go through 19 now, and then approach positive 18, because again, we've shifted it up 18. And that's the graph of this temperature function. Okay, now the part 3 was about what happens to the temperature as time gets really big. Well, we've essentially answered this question using the graph. Essentially, it's asking what happens to the graph when time goes off to infinity, and as we've discussed, it gets closer and closer to 18 degrees. It never actually hits 18 in theory, but it gets closer and closer. And this makes sense, right? You have this poor person who's died, and they're 30-something degrees. They're sitting in a room that's 18 degrees, at constant 18. So over time, if it was to sit in there for a long, long time, it's going to get closer and closer to the surrounding temperature, which is 18 degrees. Okay, so let's just say for part 3, using the graph from 2, we see that temperature T approaches 18 degrees as time goes to infinity. Let me just point out that T it's always bigger than 18 degrees. So when I say approach 18, I mean from above, just like the graph, is always bigger than 18 degrees. And in theory, of course, maybe in practice it can hit 18 degrees exactly, but in theory it never actually reaches 18 degrees. It never reaches 18 degrees C. Okay, so let's go back to the question one more time for part 4. I guess it's sort of crucial when this person died. So we know a bit more information. So we know we've made a recording of the temperature of this body at 4 p.m. and we figured out that it was 30 degrees. We need to use this formula, this function, to figure out at what time this person was murdered. So we know T, we know capital T, the temperature is 30, and now we're after little t. Okay, so let's go to part 4. We know at 4 p.m. T equals 30. So we want T equals what when little t equals what when capital T is 30. So let's go back to our function. Well, here it is. Capital T is 18 plus 19 e to the kt. E to the minus 0.859 t. So now if we substitute capital T equals 30, we want to figure out what little t is. So we have 30 is equal to 18 plus 19 e to the minus kt. And we're going to solve this for little t, and it's much the same as when we solved for k. We rearrange the equation. We're going to have to take a log because our unknown is in the exponent there, but we can figure out what little t is. Okay, so just as before, 19 e to the minus 0.0859t is equal to 30 minus 18 is 12. That tells us that the exponential term is equal to 12 on 19. So divide both sides by 19. Take the log. And so this factor times little t is the natural log of 12 over 19. And so we get little t is equal to, so divide both sides by this decimal. And then we get 5.35 roughly for little t. So at time 5.35, which is basically 5 1/3 hours, the body is 30 degrees. Okay, so now we piece this together. This happened at 4 p.m. Right? At 4 p.m., the body was 30 degrees. That corresponds to time 5 1/3, or 5 hours and 20 minutes. And so if we go back from 4 p.m., 5 hours and 20 minutes, that should be the initial time. And that will give us the approximate time of the murder. So let's just say 5 hours and 20 minutes, because remember that's 5 1/3 hours, roughly, before 4 p.m. The person was murdered. So the murder occurred at, so subtract 5 hours and 20 minutes from 4 p.m. and I believe you get 10:40 a.m.